Hello everyone, welcome to this lecture. The plan for this lecture is as follows. In this lecture, we will discuss finite fields and their properties. Specifically, we will discuss the characteristic of a field. So, let us do some warm up and see how exactly we construct finite fields. So, we will see a construction of a finite field with 9 elements. I denote set F9 by which is collection of these polynomials. So, these are basically polynomials of degree 0 and degree 1 over where the coefficients are from Z3, and remember Z3 is the set 0 1 2. Okay. So, you can see that if I consider the operation of polynomial addition over the set Z3x, then it satisfies the closure property, namely you take any two polynomials from this collection and add them, you will get again a polynomial in the same set F9. But it turns out that with respect to the operation of polynomial multiplication, the closure property is not satisfied. Namely, suppose I take these two polynomials and if I multiply them, okay, then remember then when I multiply polynomials over fields where my field is here Z3, then the degree of the product polynomial will be the sum of the degrees of the individual polynomials. So, I have degree 1 polynomial here, degree 1 polynomial here. So, that is why the sum of the product polynomial will be 2, and this polynomial is not a member of the set F9. So, that is why now what I am going to do is I am going to define a modified addition and multiplication operation, where I will be doing all the addition and multiplication of the polynomial as I was doing earlier, but my resultant answer will be computed modulo this polynomial. And if you see closely here, this is an irreducible polynomial, irreducible monic polynomial actually. So, the modified operation, namely addition and multiplication, is the following. I first do the usual addition and multiplication over Z3x, and then I do a modulo x square plus 1, and that will be my resultant answer. So, for instance, if I again perform the multiplication of these two polynomials over Z3x, as I said, I will obtain this polynomial. But now what I am going to do is I am going to divide this polynomial by my x square plus 1 and focus on the remainder. So, if you see 2x square plus 1, I can express as 2 times x square plus 1 plus 2. So, 2 will be the remainder polynomial, namely the constant polynomial, and hence as per the modified multiplication operation, the product of these two polynomials will be 2, which is now a member of the set F9. Okay. So, it turns out that with respect to the modified addition and multiplication operation, namely addition and multiplication modulo this irreducible polynomial, the collection F9 satisfies my ring axioms. Okay. Now, I would be interested to check whether this collection F9 indeed satisfies the axioms of field as well, okay, with respect to the addition and multiplication operation modulo this irreducible polynomial. And for field axioms, we need that each non-zero element should have a multiplicative inverse. Okay. So, I have to check whether every element of this set F9 except the element 0, whether it has a multiplicative inverse. And it turns out that indeed each non-zero element of this set F9 has a multiplicative inverse. So, for instance, the multiplicative inverse of 1 is 1, because if you multiply with 1 you get 1, and then if you do a modulo x square plus 1 you will get 1. In the same way, inverse of 2 is 2, because 2 into 2 is 4, and 4 you will first reduce over Z3, you will get 1, and then if you reduce 1 modulo x square plus 1 you will get 1. If you do the product of x and 2x, you will get 2x square. Now, the coefficient 2 when reduced within Z3 will give you coefficient 2 itself, and now if you reduce 2 x square modulo x square plus 1. So, you will first multiply with you will get this, and now if you do a subtraction you will get minus 2, but minus 2 over Z 3 is actually plus 1, which is the identity element, multiplicative identity. So, like that you can verify easily that under each element I have written down its corresponding inverse element, and each of the inverse element is actually a member of the collection F9. Okay. So, that means each of the non-zero element here indeed has a multiplicative inverse. So, now I want to show you some another interesting property of this field F9. So, we have already proved now that this collection F9 satisfies the field axioms with respect to the addition and multiplication operation modulo this irreducible polynomial. I have not shown you the distributive property, namely addition distributes over multiplication, but it is easy to verify that. But I would like to show you another interesting property of this field. So, here I am going to focus on all the non-zero elements of this set F9, and now what I have computed here is the following. I have computed various powers of this element 2 x plus 1, of course modulo the irreducible polynomial. So, the polynomial 2 x plus 1 power 1 will give you the same element, 2 x plus 1 whole square modulo x square plus 1 will give you x. So, if you want to verify that, let us do that. So, you have 2 x plus 1 whole square. So, you will first expand it. So, you will get 4 x square plus 4 x plus 1, but each of the coefficients has to be first reduced over Z 3. So, 4 becomes 1. Okay. So, you get x square, 4 becomes 1 again. So, you get x, and then you get plus 1, and now you have to reduce x square plus x plus 1 modulo x square plus 1. That is the way we have defined our modified multiplication operation. So, you will get x square plus 1, and now if you subtract you get x, and 1 cancels out. Now, you cannot further divide x by x square plus 1 because the degree is less. So, x will be the remainder, right. In the same way 2 x plus 1 whole cube will give you x plus 1 and so on. So, what I have shown here is if you take the various powers of 2 x plus 1 and do the and compute the powers as per the modified multiplication operation, then you get basically all the non-zero elements of this collection F9. That means, I can treat this element 2 x plus 1 as a generator which can generate all the non-zero elements of this collection F9. Okay. And as per our notation of generators and cyclic group, I can basically say here that if I consider the field F9 and focus on the multiplication operation modulo x square plus 1, then it is actually a cyclic group where 2 x plus 1 is a generator. I will touch upon this fact later, but this was just for your demonstration. So, now next we want to define what we call as characteristic of a field. So, imagine you are given an abstract field. So, this is your abstract plus operation and abstract dot operation, need not be your integer plus and integer dot operation, and my elements 0 and 1 are the additive and multiplicative identity respectively. Again they need not be the numeric 0 and 1, okay. They are the representation of your additive and multiplicative identity element. Now, what I am going to focus on is the following. I will see what are the various elements I can generate as per the dot operation from this multiplicative identity element 1. Okay. Sorry, I will be focusing on the subgroup, cyclic subgroup as per the addition operation. Okay. So, basically I am going to add 1 0 times, which will give me the element 1 itself as which will give me the element 0. So, 0 times 1 will give me 0, 1 times 1 will give me 1, and 1 plus 1 give, which is same as 2 times 1 will give me 2, 1 plus 1 plus 1 3 times will give me 3 times 1, which is same as 3, and so on. Okay. Again, I am using this, I am denoting 2, 3 as a result, but this need not be the element numeric 2, numeric 3. They are basically representation of the result of adding the multiplicative identity 1 to itself. Okay. So, if I focus on the cyclic subgroup, namely the various elements which I can generate by adding the element 1 to itself several times, then that will be a subgroup of my original group. Okay. So, remember this collection F with respect to the plus operation constitutes a group, because that is one of the axioms of the field. And since I am taking an element 1 belonging to the set F and computing the various powers, then as per the rules of group theory, this will be considered as a subgroup, and it will be a cyclic group where 1 is the generator. So, the characteristic of the field is the smallest positive integer m, such that when the multiplicative identity 1 is added m times, I get the element 0. So, why I am focusing on the positive integer, why not 0 is allowed here? Because as per the definition here, 0 times 1 will of course give you the element 0. So, that is why I am interested in the smallest positive integers. So, it turns out that as per the definition of our characteristic, if your field F is a finite field, then of course, the subgroup, the cyclic subgroup generated by the element 1 also will be finite, and in that case what I can say is that the characteristic of the field is nothing but the order of the cyclic group generated by the element 1, because whatever is the number of elements generated by this element 1, say if it is there are m number of elements, that means starting from the 0th power to the m minus 1th power, I can generate all the elements, and then as soon as I take the mth power, I will get back the identity element, namely 0. Whereas, if the field F itself is infinite, then the characteristic of F need not be well defined. So, typically we will be interested in the characteristic of a field when our field is a finite field. So, let us see some examples of characteristic of a field. So, let us first take this example, namely the field of field consisting of the elements 0 to p minus 1, that is my set ZP, and my plus operation is addition modulo p, and my multiplication operation is multiplication modulo p, and here the identity elements are indeed the numeric 0 and 1 respectively, the additive and multiplicative identity elements. So, now let us try to find out the characteristic of a field. So, for that we have to focus on the size or the order of this subgroup, namely the subgroup generated by the element 1. And if I consider the subgroup generated by the element 1, it will be the entire set ZP, because 0 times 1 will give you 0, 1 added to itself only once is going to give you the element 1, 1 added to itself again will give you 2, and so on. So, basically the characteristic here will be p, because if I add 1 to itself p times, and remember by add I mean addition modulo p. So, if I add 1 to itself p times, the result will be p, and p modulo p as per the plus modulo p operation will give me the element 0. So, that is why the characteristic of this field will be p. Now, let us consider the field that we had constructed at the beginning of this presentation, this lecture. This was the field consisting of 9 polynomials of degree 0 and 1 over Z3, and all my operations are modulo x square plus 1. Then here the additive identity is the numeric 0 or the constant polynomial 0, and the multiplicative identity is the constant polynomial 1. Now, if I want to find out the characteristic of the field F9, basically I have to find out the size of the subgroup, cyclic subgroup generated by the element 1, and it is easy to see that the subgroup generated by the element 1 will be the constant polynomials 0, polynomial 1 and polynomial 2. So, there are 3 elements, that is why the characteristic will be 3, and indeed if you add 1 to itself thrice, you will get 3. Now, if you reduce 3 modulo 3, you will get 0, and now if you do 0 modulo x square plus 1, you will get the element 0. So, that is why the characteristic of this field is 3. Now, let us consider an abstract field F4, where my elements are letters here W, Y, Z and T, and now I define an addition and multiplication operation as per this table. So, this table basically tells you the result of performing the plus operation and multiplication operation. So, for instance, if I consider this entry basically means that if I add Y and Z, then my result is T. In the same way, as per the multiplication table, the interpretation here is that if I multiply Z with W, my result is W, and so on. That is a definition, that is my definition of the plus operation and the dot operation here. And it is easy to verify that all the field axioms are satisfied. The closure property with respect to the plus is satisfied, because you take any 2 elements of this collection F4 and add them, you will get again an element of the collection F4. Similarly, dot or the multiplication is closure, and you have the identity elements here. Let us identify the additive identity element, namely 0. What exactly is the element 0 here? The element 0 here is actually the element W, because you add W to any element, you get the same element back. So, you add W with W, you get W, you add W to Y, you get Y, and so on, right. So, even though W is the additive identity, whenever I want to refer to additive identity, instead of saying W, I will use the notation 0. In the same way, the multiplicative identity here is Y, because if you see the column under Y in the multiplication table, each element when multiplied with Y gives you back the same element. Okay. So, now what will be the characteristic of this field? So, finding the characteristic of this field, since the field is finite, I will basically focus on the cyclic subgroup generated by this multiplicative identity element, namely the elements generated by various powers of y. So, 0th power of y will give me the element y itself, and y added to itself, okay, as per the additive table gives me the element w, and that is all. After that, I can't generate any new element. So, that is why, since there are 2 elements here, the characteristic of this field is 2, and indeed you can check here that y added to itself will give you the element w, which is my 0 elements, right. So, that is the definition of characteristic of a field. So, we have seen examples of 3 fields in this lecture, the field ZP, the field F9 and the field F4, and the characteristic of each of these fields is a prime number. Now, you might be wondering, is it accidental or is it in general always the case? So, it turns out that this is not accidental, and indeed this is the case for every finite field. So, we can prove the following, that if you take any finite field f with an abstract plus and dot operation, then its characteristic is always a prime number. It can't be a composite number, okay. And at least the theorem is true with respect to the examples that we had seen already in this lecture. So, now let us try to prove this theorem. So, the proof will be by contradiction. So, the theorem says that the characteristic should be a prime number, but as per the proof by contradiction strategy, I will assume the contrary, and I will assume that the characteristic is not a prime number. If it is not a prime number, it is not a prime value, then it will be composite. So, let characteristic be m, and suppose it is a composite value. Since it is a composite value, it will have prime factors or some factors. So, let m 1 and m 2 be the factors here. And none of them is actually m, because that is the definition of a prime composite number. Now, since the characteristic is m, where m is the product of m 1 and m 2, that means in the field f, the element 1 when added m 1 m 2 times will give you the additive element, additive identity is 0, right. That comes from the definition. Now, if this is the case, then I am going to prove that either the element 1 added m 1 times will give you the element 0, or the element 1 added to itself m 2 times will give you the element 0. Okay. That is what I am going to show next. Assuming that this claim is true, then this goes against the assumption that the characteristic of the field was m 1 times m 2, because if 1 added to itself m 1 times gives you the element 0, then it implies that the characteristic is m 1, or if 1 added to itself m 2 times gives you the element 0, then that means the characteristic is m 2, and both m 1 as well as m 2 are individually less than m. So, that goes against the assumption that the characteristic of the field was m 1 times m 2 at the first place. So, everything now boils down to proving this claim. That means, assuming that 1 added to itself m 1 m 2 times gives you 0, I have to show that either this statement is true or this statement is true. And again I will use a proof by contradiction to prove this claim. So, my goal is to show that 1 added to itself m 1 times or 1 added to itself m 2 times gives you 0, but on contrary assume that 1 added to itself m 1 times gives you a non-zero element A, and 1 added to itself m 2 times gives you another non-zero element, say B. Okay. Now, if that is the case, I have to arrive at a contradiction somehow. And how do I arrive at a contradiction? So, I utilize the fact that 1 added to itself m 1 m 2 times can be splitted as follows. I can say that let me add 1 to itself m 1 times, and then again let me add 1 to itself m 1 times, and then again let me add 1 to itself m 1 times, and like that if I do this operation of adding 1 to itself m 1 times total m 2 times, that will give me the effect of as if I have added the element 1 to itself m 1 m 2 times, right. Now, as per my assumption 1 added to itself m 1 times will give me a non-zero value A, right. In the same way, the next block of or the next operation of element 1 added to itself m 1 times will give me again element A, and in the same way the last operation of performing the addition operation over the element 1 m 1 times will also give me the element A. So, what I can say is that the result of adding 1 to itself m 1 m 2 times is equivalent to adding this non-zero element A to itself m 2 times. Now, what I can say is the following, since the element A is a non-zero element, okay, I can say that as per the definition of multiplicative identity, if I multiply the element A with the multiplicative identity, namely the element 1, I will get the element A itself. So, I can write A as the dot of 1 and A, and like that each of the A's I can replace by 1 dot A, and how many times I can do that? M 2 times. Now, remember I am considering right now a field, and over a field the plus and the dot operation satisfies the distributive property. So, what I can say is the following, I can take out this dot outside and distribute inside, I can collect all the plus, and how many plus I have inside M 2, because this whole operation of 1 dot A was performed M 2 times. Now, I utilize the fact that 1 added to itself M 2 times will give me the non-zero element B. That means, this value is nothing but B, and overall I get the conclusion that 1 added to itself M 1 M 2 times gives me the element B dot A, and B dot A will not be 0, because as per my assumption A is not equal to 0, B is not equal to 0, and recall in a field if you have two non-zero elements then their dot is also not 0. So, since B dot A is not 0, I get the conclusion that I get a contradiction that the characteristic of the field is M 1 M 2, because if the characteristic of the field was M 1 M 2, then the result of 1 added to itself M 1 M 2 times should give me the element 0, but what I have shown here is that 1 added to itself M 1 M 2 times is not 0, right. So, I get the contradiction, and that shows that my claim is correct, and if my claim is correct then that contradicts the assumption that I made here, namely the characteristic is a composite number. That is a incorrect statement. That means, the characteristic M was actually a prime number. So, with that I conclude today's lecture. Just to summarize, in today's lecture we discussed about the characteristic of a field, and we proved that if your field is a finite field then its characteristic is always a prime number. Thank you.